Thank you, Matthias. It's a pleasure for me to speak to all of you today. It's a pleasure to present the top 10 ways to reduce concrete's carbon footprint. This presentation is mainly aimed at concrete specifiers, but you will soon see how important it is for the entire design, manufacturing, and construction team to be ready to implement these strategies if we are going to meet our goal of reducing carbon footprint. According to the UN Environment Global Status Report in 2017, the world is projected to add 3.4 million square feet of buildings by 2060. That's an area equal to 1.4 times the entire current global building stock. The UN report urges building designers and owners to design disaster-resilient buildings for the future with zero energy consumption. At the same time, the UN report also urges the building industry to reduce the embodied impacts of the building materials they use. And because of its thermal mass, concrete has long been the material of choice for energy efficiency. And because of its strength and durability, it has also been the material of choice for disaster resilience. The challenge, of course, is to offer these concrete benefits with lower carbon footprint. This presentation will discuss how design, manufacturing, and construction teams can implement 10 simple strategies to reduce concrete's carbon footprint today. These recommendations are listed broadly in order of priority, but not in order of impact reduction. All are important and should be implemented. In addition, the strategies are meant to achieve a lower carbon footprint without impacting other traditional performance criteria for concrete. Let's start with the top 10 things you can do to lower concrete's carbon footprint. Then I will go through each one in detail. Number 1, communicate carbon reduction goals. Number 2, ensure good quality control and assurance. 3, optimize concrete volume. 4, use alternate cements. 5, use supplementary cementitious materials. 6, use admixtures. 7, don't limit ingredients. 8, set targets for carbon footprint. 9, sequester carbon dioxide in concrete. And finally, encourage innovation. Number 1, communicate carbon reduction goals. This is the most important step. One of the basic tenets of achieving a goal is to effectively communicate that goal to everyone on the team. For concrete, this is especially important because there are so many parameters and criteria for concrete mixtures. To make sure that reducing embodied carbon remains a top priority throughout the project, it must be included in the drawings and the specifications that are communicated to the owner, contractor, and product supplier. I have 3 basic recommendations here. The first is to collaborate. The only way you can set carbon footprint goals is to understand the capabilities of contractors and producers who will work on the project. Invite them for meetings with your design team. Understand that technologies and concrete ingredients are available locally. Just because a product like slag cement, for example, isn't generally used in a market, that doesn't mean you should not specify that product or prohibit its use. Generally, the reason a product is not used is because there is no demand for it. You need to create that demand by permitting and encouraging its use. Next, specify your goals or targets. State your goal at the beginning of the concrete specification in section 03300 of the specification, part 1. Make it clear that what level of carbon reduction you are trying to accomplish for the project and for the concrete itself. And then communicate that goal again in the pre-bid meetings. It is also important to communicate anytime that you get together with the design and construction team. Most projects have pre-bid meetings, which can be the opportunity for you to communicate carbon reduction goals to all the product suppliers on a project. Number 2, ensure good quality control and assurance. Concrete producers design concrete mixes to meet the needs of the contractor in terms of workability, flowability, pumpability, finishability, and so forth, based on their local aggregates and then using sufficient quantities of cementitious materials to achieve the required compressive strength, which is higher than the specified compressive strength. This over-design, that's the difference between the actual average compressive strength and the specified compressive strength, is based on well-established statistical methods described in the codes and standards for concrete. There are well-established procedures for taking concrete samples, preparing test specimens, storing them on site, transporting them to a laboratory, and finally, testing them in a compression testing machine or other apparatus. Concrete rarely tests well when testing protocols are not followed. If test results constantly show lower strength, then the only remedy is to increase cementitious material quantity, which of course increases carbon footprint. One way to provide assurance that a concrete producer has good quality control is to require certifications for their manufacturing facilities, mixer trucks, concrete technicians, and plant operators. The same can be said for installers and independent testing laboratories and their personnel. In the quality assurance section of the concrete spec, require that installers are ACI certified, concrete producers have their plants and technicians certified. These same principles apply to testing labs. Make sure they are qualified and their personnel are certified. Number 3, optimize concrete volume. This strategy is just about employing good design practices. If a structural element, such as a column or beam, is designed larger than required, then excessive concrete is being used, which increases embodied carbon. Alternatively, for a high-rise building, reducing the size of the columns might be critical to keeping the rentable space to a maximum. That means using high-strength concrete, which generally means higher carbon footprint, but it might be a well worthwhile trade-off. We suggest using life cycle analysis software to quickly calculate the embodied carbon of concrete elements, including structural and architectural elements. Consider exposing concrete wherever possible. Finished materials have a considerable carbon footprint, and since exposed concrete can be attractive and is fire resistant without the need for additional protection, this is an excellent strategy for reducing carbon footprint of the building. The other benefits of leaving concrete exposed is that concrete absorbs carbon over time through a process called carbonation, and I'll discuss that later in the presentation. Our first case study is 960 West 7th Street, a multi-family high-rise development located in the heart of downtown Los Angeles. This 64-story tower has 780 residential units, totaling 807,000 square feet. There were several challenges on the project. Projects of this magnitude have challenges when it comes to balancing cost, long-term value, energy efficiency, occupant comfort, and sustainability. The design team, developer, contractor, and product suppliers need to have the same goals in mind when it comes to reducing environmental impact, including carbon footprint. The first sustainable solution was to design an efficient structural system. Structural engineers play a key role in selecting the structural system for most buildings, especially for high-rise buildings in high seismic zones like Los Angeles. In working with the design team, to best meet the project goals, the engineering firm proposed a cast-in-place post-tension slab with a centralized buttressed concrete core that tapered with height. This system optimized floor-to-floor heights, eliminating transfers, and worked with residential and public spaces to optimize net gross floor ratios while preserving unobstructed views at the building perimeter. The firm's optimization also included performance-based seismic design and using high-strength rebar wherever it led to a material reduction. The design team set targets for carbon footprint and used life cycle assessment software to evaluate a benchmark building against the proposed building. Engagement with the contractor and concrete supplier early on also helped tighten up the mix designs, where the single challenge of the aggregate being used, moving to imported and higher quality aggregates, improved quality control, and variation in the mix performances, allowing the same compressive strength reliability to be achieved with a lower quantity of cementitious materials. The structural engineer worked with the contractor to determine where faster strength gain was really needed and adjusted testing age accordingly to accommodate higher volumes of supplementary cementing materials. The design team reduced 24% of the total project embodied carbon footprint at no additional cost. That's after accounting for the carbon from barging aggregate from the Pacific Northwest down to Los Angeles. On the post-tension slab mixes alone, they reduced carbon footprint of the mix by 47%. Number 4, use alternative cements. There are several alternatives to Portland cement, but the most common are called blended cements. These combine ordinary Portland cement with other materials. The most common type of blended cement is Portland limestone cement, often called PLC for short, or technically ASTM C595 type 1L cement. This blended cement combines up to 15% limestone interground with Portland cement to make a cement with a carbon footprint that is up to 10% lower than ordinary Portland cement, with performance that is identical to, and in some cases better than, ordinary Portland cement. There are 4 types of blended cements under ASTM C595, ranging from type 1L to type 1S, combining slag and Portland cement, type 1P, combining a positive like fly ash with Portland cement, and type 1T that combines 2 of these constituents with Portland cement. There's also another standard called ASTM C1157 for performance-based cements, which doesn't provide these kinds of limitations on the combined materials. Both ASTM C595 and ASTM C1157 have been permitted in national standards such as ACI 318 and 301, ASTM C494 for ready-mix concrete for at least 2 decades, but most project specifications inadvertently prohibit their use by not listing them in the specification. The solution here is quite easy. Just list all 3 types of hydraulic cement in your specification. Number 5, use supplementary cementing materials. Nearly all concrete used today has some amount of supplementary cementing material. The most common are fly ash, slag, and silica fume in that order. However, there are others such as meadowkaolin, volcanic ash, rice husk ash, and ground glass, just to name a few. Some are waste byproducts of other industrial processes, and others are naturally occurring materials that require little processing and therefore have small carbon footprints. All enhance the performance of concrete when combined with Portland cement, including increased strength, increased durability, and enhanced workability. There's a complex chemical process that occurs between the SCMs and the Portland cement hydration byproducts, which contributes to these enhanced properties. The solution for this one is also easy. Just list all types of cements and SCMs permitted by code and standards. There's no need to limit quantities in this part of the specification. This is our second case study. This is the University of California, San Diego, North Torrey Pines Living and Learning Neighborhood. The neighborhood will be 10 acres of academic, residential, commercial, and cultural buildings. It'll include an arts and humanities building, craft center with classrooms and specialized facilities, a social sciences public engagement building, and 4 residential buildings that will house 2,000 students. So it's a very large project. One of the biggest challenges faced for these constructing new buildings on the UC San Diego campus is the university's sustainability policy. That policy requires that all new buildings are minimum LEED silver. In most cases, they're recommended LEED gold, and the North Torrey Pines Living and Learning Neighborhood was set to achieve LEED platinum. Here are some of the sustainable solutions that were used on this project. Life cycle analysis was used by teams bidding on the project to demonstrate sustainable design outcomes. Type 1L blended Portland limestone cement with 13% limestone was used on the project. This project could use up to 31,170 metric tons of type 1L Portland limestone cement, which could save over 3,000 metric tons of CO2, the equivalent of taking 664 cars off the road for 1 year. The designers also exposed concrete for aesthetic reasons, but took advantage of concrete's ability to absorb carbon dioxide. Through collaboration and open discussion, the project teams were able to determine the aesthetic, structural, and environmental benefits of the concrete. In addition to CO2 reduction, the use of Portland limestone cement also enhanced the appearance of the exposed concrete. Number 6, use admixtures. Nearly every concrete made today uses some sort of admixture. Most affect the plastic properties in order to make concrete more workable, economical, shorten or lengthen set time, and so on. But without admixtures, concrete could not be pumped hundreds of feet in the air or transported hundreds of miles, and in many architectural finishes could not be achieved. There are water-reducing admixtures that in effect reduce cement demand, accelerators that improve strength gain, and viscosity modifiers that permit concrete to flow into very tight spaces. An example of how effective admixtures can be: using a water-reducing admixture that reduces water content in a mixture by 12% will result in a reduction in cement content by 70 pounds for equivalent slump and strength, and a carbon reduction of roughly 10% for 4,000 psi concrete. High-range water-reducing admixtures can reduce water content by as much as 40%, but the potential for reduction in cementitious materials may not be that high because of other constructability requirements. Another simple solution for this one: basically, all admixtures that meet the ASTM standard should be permitted and listed in your concrete specification, and those that do not meet a standard should still be considered with proper submittals and technical backup. Number 7, don't limit ingredients. All too often, there are seemingly random limits on material ingredients in project specifications that limit the concrete producer's ability to meet performance criteria, let alone reduce carbon footprint. Having unnecessary limits on the water to cementitious materials ratio is one example. In most cases, requiring a maximum water cementitious materials ratio is unnecessary and drives up cement content. There are times when a maximum water cementitious materials ratio makes sense, mostly for cases of concrete exposed to freezing and thawing, but it is not necessary to call it out in the specification. Identifying the exposure class of concrete per ACI 318 and ACI 301 will suffice. The requirements for water cementitious materials ratio for concrete exposed to freezing and thawing are outlined in the specifications. The same is true for air content. It's only required for concrete exposed to freezing and thawing. Air entraining decreases concrete strength. For instance, a 10% increase in cementitious materials content for 4,000 psi air-entrained concrete compared to non-air-entrained concrete of the same strength would roughly translate to a 9% increase in carbon footprint. Do not list maximum cement contents or minimum cement contents, maximum fly ash contents or minimum fly ash contents, and certainly don't limit water to potable water. There's an ASTM standard for water used in mixing concrete, and you don't need to have it be a potable water. A recommendation is to provide a table in your specification for concrete listing the important performance attributes for concrete. Each project will have different values depending on the project requirements. For this example, Class 7 concrete exterior pavements would have a water cementitious materials ratio and air content limit because of its exposure to freezing and thawing, which is spelled out in ACI 318 and ACI 301. And finally, concrete that will not be stressed for a significant amount of time can be tested at a later age, which means higher volumes of SCMs can be used, resulting in a lower carbon footprint. Number 8, set targets for carbon footprint. This strategy is for those who have some knowledge of life cycle assessment, experience with environmental product declarations, and an understanding of global warming potential for the targets to be implemented effectively. First, resist the temptation to set carbon footprint limits for individual classes of concrete. In effect, this is the same as providing prescriptive limits on materials and leaves little room for the contractor and producers to innovate and meet the project performance requirements, including budget and schedule. The best approach is to use whole building life cycle assessment to set a carbon budget for all the concrete on the building. It is necessary to have a general idea of what the carbon footprint of each mix design will be to set a carbon budget for the building, but try to resist that temptation to put a limit on each mix design. Many concrete companies have published EPDs for concrete, and the most would be willing to publish EPDs specifically for a project. NRMCA in the United States has published a cradle-to-gate life cycle assessment for ready-mix concrete and an industry-wide EPD for concrete. Armed with this information, you can conduct an LCA to determine the embodied impacts of concrete of a benchmark building using typical concrete mixes with typical amounts of supplementary cementing materials, and a proposed building using concrete mixes with higher volumes of supplementary cementing materials like fly ash and slag. Once you've calculated the carbon footprint for the proposed building, list those targets in your specification as shown here. Our next case study is the Oracle Waterfront campus in Austin. It's a corporate office building with over 550,000 square feet of floor space, with nearly 150,000 square feet of attached ground level parking garage and 650,000 square foot detached parking garage. The entire design and construction team was challenged to have the project blur the lines between public and private property and be welcoming to the pedestrian-friendly community that surrounds it, while meeting challenges of sustainability criteria of LEED and the Austin Energy Green Building standards. The structural engineers worked closely with the design build team to meet a demanding schedule, structural challenges, and the environmental criteria for this concrete building. The design required oversized floor plates to accommodate open office spaces, expansive balconies and terraces, and large meeting spaces. They also made the designer's vision for a truly unique lobby space come to life with a floating stair and bridge that lead visitors to large meeting spaces. Structural engineers conducted an LCA using software which considers the embodied impacts of all materials of the structure and enclosure for the project. Since this was such a concrete intensive project, they focused on improving concrete mix designs to meet the LEED whole building LCA criteria for lowering environmental impacts. They created 2 computer models to compare the proposed building to a baseline building, fully maintaining the functional equivalence the 2 buildings, but varying the mix designs. The improved mixes were analyzed by the software to determine the embodied environmental impacts per cubic yard, and based on that analysis, the concrete mixes were implemented into the whole building LCA. They also varied the age for testing concrete to allow for higher volumes of fly ash. For example, since the foundations did not need to see the full design load until construction is complete, they specified testing concrete at 56 days for the drilled piers. As a result, the project met the rigorous LEED whole building LCA credit by showing at least a 10% reduction in global warming potential, 12% in this case, along with at least 10% reduction in at least 2 other environmental impact categories. Strategy 9 is sequester carbon dioxide. Carbonation is a naturally occurring process by which CO2 penetrates the surface of hardened concrete and chemically reacts with cementitious or the cement hydration products to form carbonates. For in-service concrete, carbonation is a slow process with many dependent variables. The rate decreases over time. This is because carbonation decreases permeability, and carbonation occurs from the surface inwards, creating a tighter matrix at the surface that makes it more difficult for CO2 to diffuse further into the concrete. While slow, the carbonation process does result in an uptake of some of the CO2 emitted from the cement manufacturing process, a chemical process called calcination. Theoretically, given enough time and ideal conditions, all the CO2 emitted from calcination could be sequestered via carbonation. Consider permitting the use of recycled aggregates made of demolished concrete on the project, and possibly require that those recycled aggregates be exposed to air for 1 year before being used. In some cases, a certain percentage of aggregate used in concrete to be recycled up to 10%, for example, can be permitted, or it can be simply be required that all aggregate base or fill material be made of crushed concrete on the project. There are also some ways to artificially inject CO2 into concrete. So you can use a process called carbon mineralization, such as injecting CO2 into concrete or curing in CO2 environments, would also be encouraged in the specification. There's also a product called artificial limestone that's made with CO2. It is also worth considering the use of exposed concrete on the project, both on the interior and the exterior. This has the added benefit of reducing the amount of finished materials in addition to absorbing CO2 throughout the lifetime of the building. Strategy 10. Of the 10 strategies, this is probably the most challenging. How do you encourage innovation? Throughout this presentation, I've talked about the importance of not listing specific products or naming certain technologies, but instead simply list the standards that one must meet. The problem with this approach is that it permits innovation, but it does not necessarily encourage it. And many innovations might not meet a standard. The recommendation here goes back to strategy 1, communicating the carbon reduction goals to contractors and producers during the design process, which is critical. Let them know that you are looking for innovative solutions. Design charrettes would be a great place to encourage engineers, contractors, and concrete producers to get together to demonstrate or show what opportunities there are in bringing innovation to the project. Most sophisticated producers are experimenting on new formulations all the time. Ask them to discuss some of their low carbon concretes with you. In conclusion, there's really no silver bullet to make concrete with zero carbon footprint. It can be done, not at the volumes and costs demanded by today's building owners. For some concretes on a project, the carbon reduction might be 90%, others closer to 70%, and still others around 30%. All these reductions lead to concrete with a significantly lower footprint than similar projects. If you choose to set carbon footprint targets, this will lead to the greatest reduction, but always refer to this top 10 list when implementing ways to reduce concrete's carbon footprint. Thank you.